Yeah, they're all sleeping. I don't know. Should I think I can start. Okay. So yesterday I introduced the notion of naturalness, that is amounts to a structural stability of the parameters of a quantum field theory. Corresponds to the situation where the structure of the parameters of a given theory can be accounted for, is not incompatible with selection rules for some approximate symmetry. It doesn't mean, this criterion of naturalness doesn't mean that it's impossible to have situation where the criterion itself is violated, where you have parameters that are not compatible with selection rules. It just distinguishes, it just allows us to distinguish these two situations. One is structurally robust and the other is not. And well, we will see when we get to talk about the standard model. Okay, so again, the arena where I always be working is an effective field theory where there are two wildly separated scales. Some UV scale is the scale where our theory emerges, and some IR scale where the theory enters a new regime, and then you could go on. This pattern could be reproduced virtually forever. Okay, well, or until you reach a gap and there's nothing. And the system in between these two scales, as I argued yesterday, just by assumption, or almost by assumption, is described by an approximate conformal field theory that is a small deformation of the conformal fixed point. Okay, and okay, so and lambda I, in principle, an infinite set of parameters describe our effective field theory, aside of the particle content and the very theory itself, the very fixed point. Our theory is defined by the CFT, what it is, what the data of the CFT, plus the infinite set of perturbations. Okay, the data of the CFT is just the operator dimensions and the 3-point functions. Okay. Now, in this situation, every observable that we could compute at energies below the defining scale is just a function of these parameters, and in particular, the very infrared scale itself is a function of these parameters. And so it's licit, according to our discussion of yesterday, to ask the question: is the separation lambda IR much less than lambda? That is our defining assumption. Is this assumption natural? Okay, that's the question. So under what conditions my hypothesis, the hypothesis that there is this scenario is robust? Okay, it is compatible with selection rules. And as an example of something unnatural, I already showed to you yesterday, okay, a situation where you have the effective theory is just a scalar field plus all possible interactions. So a licit question here is, so in this situation, the IR scale is basically the mass parameter, okay? And so you can ask under what condition can this object be much less than the defining physical cutoff, okay? And we argued that just by selection rules, that is, in our case, is dilatation symmetry and the shift symmetry that is broken by this parameter, we expect that m square, scales lambda square, this is dilatations, selection rule, times the other parameter that you need to inform the field itself that the shift symmetry phi goes to phi plus constant is broken. So this is the shift symmetry. And there can be a loop factor, okay, 16 pi square. I'm being very cavalier with that, okay? So that's basically the expectation from structural naturalness. And in those situations where this mass is much less than that, given lambda, given the two lambdas, the little and the big lambda, we think the situation is, we define the situation as unnatural. It doesn't mean it's impossible. It's just not following directly from selection rules. It's a very clever choice of parameters that you could not guess from the PhD student generalization of dimensional analysis that is selection rules, okay? Dimensional analysis is the first thing we learn in physics, and somehow it seems like we want to use it. Perhaps at a certain point we will have to give up. Okay, so let's consider the situation, and let me. It's useful to address the question, okay, in the language of our G flows. Okay, so what do we have? What do we have in this scenario? We have a theory that starts in the UV at some point. Okay, and this point is not far from a CFT fixed point. When I say CFT, it could be only scaling variant, but I'm just using the hypothesis that all scaling variant theories are conformal theories. So we start near here, and then we flow. Okay, we can flow. And how do we picture? Okay, we flow, and how do we picture? So we flow in momentum scale. Okay, let me call it Q. Q is our momentum scale. Q is our G scale. Okay, and our G time is log of lambda over Q. As we flow towards the infrared, okay, so we can view the RG evolution as a time evolution in RG time. And how do we picture? So we, as we flow, at a certain point, Q will be of order lambda IR. How do we picture this point? Okay, well, the point Q equal lambda IR is, roughly speaking, the point where the distance from the fixed point becomes of order 1. Okay, lambda I, some lambda I becomes of order 1. Okay, so this is when you reach this distance from, you can characterize on your RG clock, say, look, change your description. Okay, the point where you have to do that is where some of these perturbations become large. Okay, this is your IR. Perhaps I should specify this a little better. If you want, in a more formal way, the IR scale can be defined as the scale where the matrix elements of the divergence of the dilatation current, T mu mu, become of order 1. Okay, that's the totally well-defined definition, free of ambiguity on the normalization of couplings. Okay, so and that corresponds, if you want, in terms of beta functions, more than in terms of couplings, to the point where the beta functions become of order 1. Okay, you could imagine a situation where the coupling becomes large, where the deformation is large, but the beta function is small. For instance, if you have an exactly marginal deformation, then the deformation can become large, but the beta function is 0. So the occurrence of the new scale is the point where the beta functions become large. Okay, and so having picture. In fact, let me give you some examples. Okay, before going examples, take for instance QCD. Okay, QCD, the relevant coupling that you can define here, the running coupling as a function of Q, is alpha S over 4 pi of Q. Okay, is the loop expansion parameter, and the IR scale, and is also the parameter that controls the beta function. When this becomes of order 1, the beta function becomes large, becomes of order 1 in the suitable unit, and the IR scale is defined as the scale where alpha becomes of order 1. I mean, all my lecture is squiggly. Okay, I apologize for that. You're probably not used to it, but it's all squiggly. Okay, it's all qualitative. Or in fact, you can describe in the same language the situation where you have more traditionally a mass parameter. Okay, let's say like a fermion or a scalar mass, and this mass parameter, let's say the theory is weakly coupled. The mass parameter will evolve slowly because the theory is weakly coupled. Is weakly coupled, but the true measure of how much this parameter breaks scale invariance is given by dimensionless quantity. It is m over q. Okay, this is called lambda mass, the running lambda mass. Okay, and again, not surprisingly, the point where lambda bar becomes of order 1, lambda bar order 1 corresponds to q of order m of q. Well, okay, q of order m. Okay, so just to make, so you can describe under all circumstances the point where you step into a new description as the point along the RG flow where you have gone too far from the fixed point. Okay, far means order 1. Okay, so having depicted things this way is now obvious on how to characterize under what condition is the separation between the UV and the IR scale natural. Okay, so the separation, when the separation is large, say lambda UV over lambda, let's say middle call UV, much bigger than 1, amounts to the statement that the RG time associated to the IR scale, that is to say logarithm of lambda over lambda IR, is much larger than 1. Of course, this is power, this is a log, but still, okay? So a big separation of scales corresponds to a long RG time needed to escape the region of attraction of the fixed point. So a natural hierarchy has to do with the stability of the fixed point. The slower, the more stable the fixed point is, the longer you linger in its neighborhood, the longer it takes in RG time to reach the point where your original structure is discombobulated, where T mu mu is of order 1, and where you enter the new regime. And so for the longer this time, RG time, the wider the separation. And so it's clear that there are two, it's clear, okay. Well, perhaps it's not clear, that there are two situations where this state of things is natural, okay, and they can be characterized the two ways. One is, let me call it one. So there are two situations, okay? One is marginality. Let me call it marginality. Marginality is, I call that situation in which all the relevant, so let me say it better, the CFT does not possess any strongly relevant deformation, okay? Just structurally, okay? That's very much in line with the discussion we were having the other day, okay? You can imagine a CFT that does not contain any operators of dimension strictly less than 4. It may contain marginally relevant, it may contain irrelevant, and it may not contain very strongly relevant operators. In this situation, it is enough a small seed of smallness in the boundary condition at the ultraviolet scale to generate a big hierarchy. And the quintessential example, so in fact, let me say it better. Is to say dimension strictly less than 4, say 3, 2. Okay. Let me give you let me show you the quintessential example of this. Okay. Quintessential example is Yang-Mills theory. Okay. In Yang-Mills theory, the suitably normalized deformation lambda is g squared over. Did I get? Perhaps I missed a factor of 2, but and the beta function is the evolution with respect to the normalization scale is this plus higher orders. Okay. So here you are in a situation where the gauge coupling is associated with a marginally relevant deformation. This is an operator of dimension slightly less than 4. In fact, it's less than 4 only when the deformation itself is 0. Strictly speaking, at the fixed point, at the exact fixed point, the dimension of the deformation, that is the gluon kinetic term, is 4, exactly 4. But as soon as you turn on the coupling, it acquires an anomalous dimension, becomes slightly relevant, and therefore its importance grows in the infrared. But you see, the importance it acquires goes quadratically with the coupling itself. Okay, the very fact that here you have a square and not a linear power is associated with the fact that, see here in the case of this object here, the derivative with respect to q of m of q is equal to minus 1 plus the anomalous dimension, in fact not m of q, but lambda bar of m. So here you have a linear relation associated with the fact that already in the limit where the mass is 0, there is a dimensionality. Okay? The operator has dimension 2 already at the fixed point. Well, here at the fixed point, the associated operator has dimension exactly 4, and so the evolution starts more slowly. It starts at second order in the deformation rather than at first order, as it happens in the case of a mass. In the case of a mass, it starts at first order, and you dash out of the fixed point. Okay? In this situation, okay, unless you start very, very close to the fixed point, okay, close, how close? Well, in order to have a hierarchy of order lambda of this thing here, say in this situation here, the original value of your deformation lambda mass in the UV should be of the order of lambda IR over the UV scale. Okay, so the hierarchy you get is exactly what you get is what you put in. If you want a hierarchy of 20 orders of magnitude, you have to start with a deformation that on the scale of your theory in the UV is 10 to the minus 20. Okay, I said 10 orders of 20. Okay, whatever. Okay, so while in this situation things are different. Okay, in this situation the evolution is slower, and so you solve the equation. Okay, the equation, as you know very well, this is where UV is the value at the UV fixed point, and this is this is the solution to the RG equation, and now you can ask under what is the value of Q for which lambda becomes of order 1. Okay, so lambda order 1 implies, and you can easily get it from there, is the okay, here you have to well, you can solve this equation, okay, and ask for lambda be of order 1, and the condition is that the scale where this happens, that is to say that the IR scale is related to UV scale by an exponential. Okay. Perhaps I should write it in a different way. Let me write it in a better way so you see it right away. So let me write it with the inverse, okay? 1 over lambda is equal to 1 over lambda UV plus 2 log of Q over lambda, okay? And imagine you start, so if you want this to be, imagine you start with some slightly small lambda UV, okay, so that this quantity here is large, and you want this quantity here to be of order 1, then there should be a cancellation between these two quantities here. In other words, this should basically reduce 1 over lambda UV to be of order 1. So basically what you want is 1 over lambda UV plus 2 log of Q over lambda to be about 0. Okay? Okay? And that's it. And this is basically this relation here. Okay? So this is a well-known property of theories with marginal couplings, and you see what this result implies. It implies that it's enough, a very small seed. It's enough for your original deformation to be not small, but not hierarchically small, but let's say algebraically small. Let's say lambda is 1 over 20, okay, 1 over 10, okay, to get an exponentially large hierarchy, okay. And that is the reason why, for instance, we don't worry about the position of the QCD scale compared to other scales in physics, okay, because it arises from a phenomenon of this type. In fact, it's not exactly that, as I will say in a moment, but that's basically the reason, okay. And phenomena of this type are widespread in condensed matter, okay, so BCS, and so separation of scales generated by theorists that have, for some structural reason, only marginal element operator is one way to naturally generate big hierarchies. Mind you that there's still the need to input a small seed, okay? So if lambda were order 1 already at the UV scale, then everything would collapse at the same scale. There's always the need to input some small parameter, but the small parameter is not so small. So we may consider that acceptable. Another example, okay, of this sort of example number 2 can be pictured in a more abstract conformal theory, imagine is just slightly damn it. Okay, it's a variant of what I wrote here. Perhaps I should write it here. Perhaps I should write here. So a variant of this situation can be pictured in an abstract conformal field theory. Imagine you have a CFT where the lowest dimensional scalar, okay, where the lowest dimensional scalar primary has dimension O, it's O, has dimension 4 minus epsilon, okay, where epsilon is an algebraically small number, let's say 0.1, just to get an idea. Why? I don't know. I mean, there is this small number that comes out of God knows where. It's small, 0.1, but it's not 10 to the minus 20, okay? And in this situation, it's possible to have the same phenomenon, an amplification of the separation of scales. Just a small seed, a small number, generates an exponentially large number. In this situation, the Lagrangian, okay, of our system between the two scales is going to be our CFT Lagrangian, plus this deformation with a coefficient that's numerical, and then it's scaled by the only scale we have in the problem, that is to say the defining physical scale of the system. Okay? Or I forgot to say, this is the situation, this scenario I'm discussing here is the holographic interpretation. I mean, this situation here occurs in the holographic interpretation of the Randall-Sundrum model. Well before ADS hydrodynamics, well before ADS CMT, there was ADS BSM, okay? And this was the Randall-Sundrum model with radius stabilization according to the Goldberger-Weiss mechanism. For instance, this discussion that I'm presenting here is, for instance, you can find it in a paper I wrote with Zaffaroni 15 years ago. Long time. Okay, we're still here doing the same things. Okay, so under this situation, you can very quickly guess what is the IR scale of this system. What is it? I'm doing like Mariangela. You can do it at a physicist way, or you can do it using you can do it using the machinery of conformal field theory. Okay, doing conformal perturbation theory. That's the way a string theorist does it. That's not the way I would do it, but if you really want to, any guess? I'm doing just because I want to drink. Okay. Yeah, but that's not fair. Okay, but let's see. This is okay. That I should have given you the hint. Yeah, sure. That's. I mean, this is the computation of a phenomenologist, and you don't have to think too much. That's not 3 loops on the disk with. Any guess? So let me. So if you do. So for instance, imagine there is an operator. This is the way conformal field theorists would do it. Imagine there is an operator O prime, such that it has a 3-point function with O of order 1. It will exist, right? I mean, for this to be part, otherwise I would just be joking. So there's an operator that has this property, and now you can ask, using conformal perturbation theory, so you can do first order perturbation theory in the parameter in this perturbation, and ask yourself at what length scale this perturbation will affect the 2-point function of O x0 over such that this is of order 1. That's the way you would phrase it, right? You have a conformal theory, you have perturbed it, and now you look at some, you want to know at what scale the perturbation becomes of order 1. That's if you want, that's the scale where you really have perturbed at order 1 your system, and that should be identified with the new physics scale, okay? With the IR scale generated by this term here. I mean, it's just, once it's stated this way, it's pretty obvious that this perturbation here, this thing here, it's something like C lambda to the epsilon, x to the epsilon. Okay? And sure, no, this is the way I would do it. No, but this is for the TASI school. No, this is for this tree. Sorry, this. I mean, no, because otherwise, if everything is too squiggly, this is the NLO squiggly. I mean, this is the. Okay, this is just to tell you, and now you can test when this is of order 1. You know what the scale is, and therefore the scale is. Where do I write it? Sorry, my way of using the space in blackboards, I really have to improve it. Okay, well, no, please help. Okay, so the scale is, the IR scale to the epsilon is C lambda to the epsilon. Okay, that's the obvious. And therefore, lambda IR over lambda of the UV scale is C to the 1 over epsilon. And now you see how, by a little bit of hocus pocus, I can get pigeons out of my sleeves. Okay, I have C, let's say that C is of order 0.1. Not that I understand why, but epsilon is of order 0.1 just by some accident. Okay, imagine, well, I don't imagine there's a landscape, but you don't need a big landscape to be in a situation like that. Okay, you don't need a very good lab technician to be in this situation if you are in condensed matter. And then out of algebraically small number, you generate hierarchically exponentially small numbers. Okay, and that's just a version of that. So that's, for instance, the way the Randall-Sundrum model works. In that situation, you have the mechanism in 5 dimensions posits the existence of a scalar field in ADS5 with a mass, slightly relevant field with a mass of order m squared times LADS of order epsilon. Okay, in fact minus epsilon. Okay, you want it to be slightly relevant. In fact, there's even models where it's like okay, that's if you take the model, this model of Goldberger-Weiss, you can reinterpret it precisely in this way. Okay, that's another example. Okay, so this is the first class of natural hierarchies. Where do I put it there? And let me now come to the second class. Now, you had many more, right? We should probably try to see in what sense things get packed into the same classes, okay? So the second class has to do with symmetry. Okay, symmetry means that the CFT does possess relevant deformations along with marginally relevant deformation, but all the relevant deformations are all they all transform under approximate global symmetries. Under global symmetries of the CFT. So the CFT possesses some global symmetry. So the fixed point, the CFT has the conformal group plus a global symmetry group. And it possesses relevant deformations, but all the relevant deformations transform in non-trivial multiplets of the global symmetry group. Okay? So in this situation, you can demand, okay, according in line with 12 naturalness, that the coefficients of this deformation that are coefficients that can be seen as that are tensors that transform under the symmetry be small. Okay, if these are the only breakings of this symmetry, selection rules will not change the state of will allow this state of things to be stable under quantum corrections. Okay, so if and that is the situation of QCD. Okay, QCD is a situation like that. Okay, QCD you have the Lagrangian. Okay, so the example here is QCD. In fact, let me take it here. Let me do it here. QCD. In QCD, you have a marginally relevant deformation. So you have so QCD is a free field theory. It's a free CFT, free gluons and free quarks, perturbed by the gauge coupling and by quark masses, psi bar m psi. Okay, that's QCD. Now, this deformation is relevant, is dimension 3. However, there is the corresponding operator transforms, okay, transform under a symmetry, chiral symmetry of the unperturbed theory. Okay, if you assume that it is consistent, okay, to assume that the theory at the scale lambda, for some reason, is endowed with the symmetry, okay, for reasons that we may be able to explain in a moment, but for some reason is endowed with the symmetry. The symmetry may originate as an accidental symmetry from a previous life of our theory, a life at higher energies. Okay, and if this situation is realized, then the request m much less than lambda is natural. Okay. In fact, QCD does even more than that. In QCD, the mass of the lightest quarks are even smaller than lambda QCD, so it's really realized full Monty. Okay. Okay. So let me give you an example of how this could occur. Okay. How could this occur? How could this approximate symmetry arise as an accidental symmetry? Okay. Well, that unfortunately, it's easy to realize. That's precisely what happens in Technicolor. That's in fact one of the problems of Technicolor. It could be that in a theory like that, at the scale lambda, below the scale lambda, this theory merges into a bigger theory, gauge theory, and in these gauge theories, quarks transform in, unlike in QCD, they transform in chiral representations, okay, in such a way that you cannot write a dimension 3. You cannot write a mass term involving just a pair of quarks, okay? It could be they transform into some chiral representation. And imagine that this theory doesn't even have scalars, like in Technicolor, okay? But it only has fermions. And in this situation, it takes very little to realize, I mean, under this circumstance, okay, if these quarks are chiral in the above theory, it could be that the leading operator, quadratic in depth size and not involving any derivatives, is a 4-fermion operator, okay? So for instance, it could be that in this scale here, a new gauge symmetry, okay, above lambda, okay? So imagine there is a scale, in fact, let me write it better. There's a scale lambda, there is some lambda prime in the UV, even bigger, and then there is our lambda IR. Now, a lambda IR is controlled, for instance, by the quark masses or by the QCD coupling becoming of order 1. But now I want to motivate the fact that at the scale lambda, the quark masses are small. Okay, I can imagine, and that's precisely what happens in Technicolor, that the theory above scale lambda is a gauge symmetry. And in this gauge symmetry, the quarks are chiral. And the only operator I can write that eventually can give rise to a mass of the quark is the following object here. It is the operator giving mass is given by psi bar t bar psi, where these t are the technique quarks. That's the only way to write. I'm not writing the indices. I'm even going beyond what John was saying. I'm not even putting the dots. Okay, there are indices all over the place, and the indices are there, and they guarantee that you cannot write an invariant with only psi bar. Okay, because these are in chiral representations, and this is a dimension 4-6 operator. Imagine the theory between here is approximately free. Okay, like in QCD, then this thing here is expected to be suppressed by the bigger scale, okay, in the previous life, and as a result, at the matching scale where the QCD theory emerges, I have an accidental symmetry. That's chiral symmetry because the only operator that breaks it comes at dimension 6. Okay, and if there is a big separation here that may arise perhaps from the first mechanism, marginality, okay? If there is, again, a big separation, I have an accidental symmetry, and this accidental symmetry will precisely become the chiral symmetry of my energy theory because, let's say, at this scale here, the technique quarks confine, and this object here in the theory below lambda will boil down to the following effective term, psi bar, lambda cube. That's the scale of condensation of those, lambda prime square psi. So just as an accidental, I have now a history, a story to tell you for why the quark masses can be small, okay? And this quark masses in this picture is of the order of lambda cube divided lambda prime square. And again, if there is a scale separation, this is much, much less than lambda. Okay. In fact, this is a sort of seesaw feature. The infrared scale now is characterized by this ratio of the intermediate scale and the UV scale. Okay. So again, this is just to tell you that the explanation of a structural property of parameters, in this case associated with the hierarchy, in terms of symmetries, does not explain the choice of parameters, but it makes it more plausible. And more importantly, it sets, as is shown in this example, it sets the stage for a dynamical explanation. Okay, so this is why symmetries are important. I mean, 't Hooft naturalness, yeah, I mean, it's certainly a guideline, but it's more than a guideline because in practice, at least in my experience, this always happens that whenever you have a symmetry explanation, you can think of a deeper explanation where that symmetry that you are invoking arises accidentally. Okay, and this is, for instance, the way I argue when I try to motivate what we do to condensed matter theorists. Because if you tell them we use 't Hooft naturalness, you say symmetries, they say, well, why? I mean, they have lab technicians to do all the, I don't know. But No, of course they do understand it, but yeah, okay. Okay, and another example of this type is given by supersymmetry. Okay, supersymmetry is so you precisely of this type. Okay, where you have you have the CFT Lagrangian is supersymmetric. Okay, you can imagine the CFT Lagrangian. Let me give you another example. Example 2. I think it's time to use the. Okay. So I'm roughly. Oh, so what is this? Okay. So example 2. Okay. Example 2 is supersymmetry. To make a long story short, in that case, the Lagrangian is L CFT plus SUSY. It's a supersymmetric CFT. Could be free. Okay. Could be interacting. Okay. And then the deformations are apart from marginally relevant deformation that you may have here. You have, for instance, quark fermion masses. Okay. I don't need to tell you what the quarks are. Okay, your fermion masses, these are operators of dimension 2. So they're relevant, but they break supersymmetry. Of course, supersymmetry is a symmetry, so you may, exactly like in the case of chiral symmetry, say, well, no, this is very, very small. For some reason, supersymmetry breaking effects are small. Okay, and this is why this is small. And in fact, okay, that's fair as far as tough naturalness goes. But again, it sets the stage. This situation sets the stage beautifully for a dynamical explanation. As we know very well, supersymmetry, because of non-renormalization theorems, is either broken at tree level or it's broken non-perturbatively. If you are in a situation where a tree level cannot be broken, just structurally, then it will be broken non-perturbatively. And in a weakly coupled theory, that means that the scale of breakdown will be exponentially suppressed, very much like the QCD scale. Okay, so SUSY broken non-perturbatively. Let's say we are in a situation where the relevant non-perturbative dynamics happens because of some marginally relevant coupling that becomes larger in the infrared, and then in this situation, the SUSY breaking scale will be of the order of the cutoff scale times y 1 over g squared, the coupling at the cutoff. Okay, this is just what happens. So again, we are precisely in a situation where we have a symmetry explanation, but we also have a dynamical explanation. Okay, so now I had foreseen a little detour into trying to illustrate all these ideas in a concrete case, that is the pion mass. Okay, precisely how all these comments are realized in a natural scenario, that is in a natural situation, that is the situation of low energy QCD pion mass. I think I have to skip it. I may come back in the discussion if somebody is interested. In fact, ask me about this. If you don't have question, I will discuss this. Okay. If not, then I will discuss something else. Okay. So I think it's time to clean, and now I want to go to physics. Okay. To the standard model. Any questions? gonna take forever. I'm not erasing everything. Let me do this because this is. Okay, so I think I'm now in a condition, I hope, to start the second part of my discussion that concerns the standard model. We now apply these points of view, try to apply them to the standard model. Okay, so okay. So what is the idea? So the idea is that the standard model is an effective field theory with a cutoff lambda, okay, which could be, I don't know, M string, the mass of the right-handed neutrinos, the mass of grand unification, God knows. The mass of flavor could be, perhaps there's a scale, some definite ultraviolet scale. Okay, definitely such a scale must exist. In recent years, there's been a lot of discussion about conformality, solving the problem, saying that there is no scale, blah 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 blah. Okay. Well, certainly there is a scale, the Planck scale, okay? That's undeniable that you do graviton-graviton scattering, even you do electron-electron scattering with graviton exchange. This process has a scattering phase that becomes of order 1 at a given scale, okay? Just do the partial wave decomposition. So that's very much like in pion physics. We can guess that there should be some new degrees of freedom at that scale. Okay, so the scale exists, okay, as a dimensionful parameter. So there should exist a scale. In fact, there have been even an interesting attempt by my friend Strumia to avoid the situation, truly have a theory that looks like a theory without scales. Perhaps I will have, if I can, I will spend some time later on discussing it. Okay, it doesn't work. Okay, but it's an honest incarnation of things, okay? And so there's a scale, and so given this scale, the idea is that we write all the terms we can write compatibly with the gauge symmetry, and maybe some global symmetry, approximate global symmetry that we may want to impose. Okay, so the idea is to write all that we can write, and let me do that. Okay, let me not write everything because it would not be enough 6 blackboards to write all the operators. There are infinitely many. But let me just organize. So let me discuss the general standard model Lagrangian in an expansion in 1 over lambda. Normally, when in textbooks, when you say standard model, you say that they're normalizable Lagrangian. It's enough. It's time to stop with that. Okay, the standard model is defined by gauge symmetry and particle content. Okay, and then it's an effective Lagrangian. You write whatever you can write, and then it's up to the experimentalist experimentalist measure which parameters are there and with which size and how. Okay, so the Lagrangian is, let's organize the Lagrangian in a power series in lambda. Okay, and let me start from the most famous part of the Lagrangian. So let me write like this, L. Let me just do like this. Right. So this is the Lagrangian. This table is the Lagrangian, so I don't need to write L. So let me start instead with the most famous part, which is the d equal 4 terms. Okay. At d equal 4, we have what? We have the gauge kinetic terms. I'm again very squiggly. there are the matter kinetic terms. There is the Higgs kinetic term. There are the Yukawa couplings. There is the Higgs quartic. Is there anything else? Dimension 4. No, there's nothing. I'm cheating. Yeah, there is something else, but there's theta, but that's, forget. There is this, okay? I'm just a naive guy, total derivatives are 0, okay? But we'll get to discuss that. Okay, this is all there is at the d equal 4 level. And it's remarkable that all the things that we have here, every single thing there has been seen and measured and tested with the varying degrees of precision that can range from 10 to the minus 10 for the G minus 2 of the electron to 10 to the minus 3 for the W Z mass difference, stuff like that. You don't agree with 10 to the minus 10? It's 10 to the minus 9?
I was wondering if we've seen H to the 4th.
Sure, we have seen. We have seen the Vev and the mass. We have seen the Vev and the mass. I mean, you could have said until a little ago that we have seen only one combination of the parameters in the. We have seen both of them. We have seen both of them. I mean, if you in the theory, you've seen the Vev and the mass, so we have seen it. 0.18. Yeah. Okay. Fine. Yeah. Well, it depends whether you put the 4 pi. The 4 factorial, or depends on what you do, right? I mean, in fact, the good thing to measure is m top over m Higgs. That's the truly good parameter. Okay, I mean, if you want, it's not that. I mean, it's in the ballpark of everything else. Okay, so here we have seen everything, and that's all. And it's also what's remarkable is basically all that we have seen. And now you can ask yourself what happens when you go down. Okay, in dimension. Okay, up in dimension. Okay, well, or down in powers of 1 over lambda. Okay, as soon as you go here, you go, say, for instance, to dimension 5, you start seeing things. As soon as you go to the so-called irrelevant operator, you start having things that we either haven't seen, luckily, like proton decay, or things like neutrino masses that took decades to see. Okay. So very tiny effect or effect that have not been seen. Let me just list them. Okay, so you have, let me just use the same notation here. You have neutrino masses, Li, H, Lj, H over lambda. That's neutrino masses. When you go to dimension 6, at dimension 5 you only have that. When you go to dimension 6, you start having like dipole operators, chi j, L bar, I, sigma mu nu, Ej, H. Sorry, this is E, and this is L. This is the doublet, this is the singlet, this is a doublet, doublet, doublet. Okay, indices are all gone. Okay. Sure, flavor. Yeah, I should put. Okay. Okay. This is also dimension 6. This is dimension 6. Then you have, for instance, I think indices are important here. JKL, for instance, Q bar, gamma mu I, QJ. This, for instance, is the doublet of quarks. QK bar, gamma mu, QL, again divided by lambda square. And more things, you can have operators mediating proton decay. Let me call this 1, and this is 2. It's complicated. Proton decay is complicated. There are too many. I have to put the epsilons. Okay, it's, let me say it, Q cube E. Okay, that's my proton decay. That's and so on. In fact, also other things. You can also have operators like this one that, let's say, let me call it C over lambda square, H dagger, d mu H square. Let's say kinetic terms, correction to the kinetic term of the Higgs involving 2 derivatives, but 4 powers of H. Okay, you can have all stuff like that. And it is remarkable that as soon as you go into this territory, you find all extraterrestrial beasts, okay? Well, the only non-extraterrestrial beast you find is the neutrino masses. It's from the moon, okay? It's not from Earth, but it's sufficiently close that we have seen it, okay?
From the sun.
No, okay, I'm just from the sun, from the sun, from the atmosphere. So it's but everything else is weird. So here you have, as soon as you go to dimension 6, you have operators that violate. So let me just call this up. Let me give them names. Let me call this 1, 2, 3, 4, and 5. And let me comment on what these things do. Okay. So the first one, of course, generates neutrino masses, and it's interesting. It's interesting that in fact, let me compare this remark that the neutrino mass come at dimension 5 with what we see in nature. Okay, let me just make a little comment on fermion masses. So fermion mass in the standard model, the spectrum, is as the following structure. You start with the top, about 10 to the 2 GeV. Then you have an array of things. You have the charm, bottom, you have strange, muon, tau, okay? And you go down to the electron. That is about 10 to the minus 3. This is GeV. This is GeV. Okay? So they're spread over a range of order 10 to the minus 5. Okay? So, I mean, there is an interesting structure. Okay? They're not coming. Well, it depends how you look at it. Just sure, it's okay. A range of x or 1 of x. You're right. Okay, let's call it this way. Is that the range of the inverse masses? No, it's the same. Okay, it's okay. So they're spread over 5 orders of magnitude, and then before finding the next guys, the neutrinos, the neutrinos, as far as we know, the neutrinos are first of all, there's an absolute upper bound on the neutrino mass is about 0.2 electron volt from cosmology, from structure formation, okay? And then, so it's about a fraction of electron volt, let's say 10 to the minus 10 GeV. So what you have is from the last seen guy, the electron, to the next neutrino. In fact, it could even be less than that, because the neutrino mass differences are about an order of magnitude below, okay? A factor of few below. So anyway, here you have a jump of 7 order of magnitude, okay? Look, let me do it this way. I prefer this way. Sorry, guys. Okay. You go down. You're going down. Okay. You go down 5 order of magnitude, then you go down 7. And you just go down, and there is nothing, okay? And, well, I think this picture is telling us, at least telling me, that the origin of these effects, the neutrino and the fermion masses, are different, okay? Of course, people criticize and say, well, but you saw even here we have big separations. Well, not so much, okay? Yeah, the separation between the top and the electron is large, but the indication is that the seed of the separation is small, because from the top to the charm is 2 orders of magnitude. So in the quark and the lepton, in the charged leptons in the quark sector, things speak in favor for some parameter, some mechanism where the seed of the structure is about 1 or 2 orders of magnitude. For instance, it could be that the quark masses come from loop effects. The top is at 3 level, the bottom has 1 loop, and the strange is at 2 loops. Okay, and you can build models of this type. They are ugly, but that's an idea. While here you really plunge by 7 orders of magnitude, and this is a structure that perhaps it speaks nicely to an engineer. Okay, somebody used to work with radios, familiar with multiple expansion, where you have good signals coming from dipole reception, and if you have a quadrupole, then you don't receive well because the coupling is done by an extra power of 1 over lambda. Okay, very much like in this case. Here, then the suggestion is very much in line with what you see here. You have the quark masses coming from dimension 4, the analog of a dipole, and the neutrino masses from dimension 5, the analog of a quadrupole. Okay, this, if you have to explain to engineers, they understand it right away. And that's very much in line. However, it's much in line with the assumption that, however, the object you're looking at, like in the engineering case, like the radio, is much smaller than the wavelength you're considering. In other words, that the structure of the object, instead of the radio here, you talk about the underlying theory, lambda is 1 over lambda is much smaller than the other scale, that is the weak scale. Okay, so this structure speaks in favor and in fact, if you plug in numbers, okay, if you take this coefficient here to be of order 1, let's say of the order of lambda top squared, it could be smaller, but again, for instance, if you take it to be of order 1, then lambda, so Yij order 1, you explain what you observe if lambda is 10 to the 14 GeV, which is quite interesting as a scale, okay? It's a scale that is not so far away from the string scale or Planck scale, string scale better, or the gut scale. So it falls into an interesting range of energy where it looks like we perhaps should expect something. So it looks like neutrino mass suggests that the next layer of the onion is very high up, and similarly all these other things, okay, to a different degree. So for instance, if you consider take for instance operators in class 2, let me erase this. I'm giving up doing everything, so I'm now going relaxed. Okay, before I wanted to finish. Now I cannot do it, so I'm much more relaxed now. I can. So let me give you the example. Probably you already know these things, but it's I don't know whether you've taken course in the standard model but the course in standard model, aside of all the details, standard model is primarily understanding why. What is. In fact, in many cases, you hear, the discovery of neutrino masses is the first discovery, the violation of the standard model. Okay, that's too much and too little. It's not a violation of the standard model. It's an operator is there. You have everything. It's only if you think stupidly that every theory has to be renormalizable, you say it's a violation of the standard model. But it is much more. It is the first time within this context that we see a new scale since the time of Becquerel. Okay. The beta decay was not Becquerel, was alpha decay. Anyway, between Becquerel and Rutherford, okay. Those days were still people dressed in a proper way, okay. So it's still very far away. So it's a huge discovery, okay. It's not just an extension of the standard model, violation of the standard model. The standard model accounted perfectly. In fact, that's precisely a success. The neutrino masses are a great success of the standard model. Okay, in that sense. Now, then you go to the other guys, the 2 case, and then you have all sorts of other things. For instance, you can have mu to E gamma. Okay, this is compatible with what you have here. In the standard model, this is 0. Okay, in the standard model, sorry, you see this at the level of dimension 4, this is 0. At level of dimension 4, this is 0. It's also 0 experimentally. Okay, that's very important. Experimentally, is not 0. Is less than the branching ratio. Now is less than 10 to the minus 13. Is it correct? Is 13? it's improving slowly with the years, okay? And there are proposals to go to 10 to the minus 15. There is a Japanese proposal to go 10 to the minus 16. Anyway, you see what it means, okay? You have to produce muon, and 1 in 10 to the 13 control that it doesn't do that, okay? I mean, that's quite non-trivial, okay? And you can think what the standard model backgrounds for these are, okay? But so, for instance, there is the decay of muon to electron, neutrino to neutrino, and photon. And the neutrinos are in the end point on the spectrum, and you don't see them. Okay, so that's important. That's the main source of background. So it's a very delicate experiment.
Would there be some small standard model background, effect actually through a neutrino link?
Sure. Oh, you're right. Right. Joe is right. Once you have this, there is this effect, but right. But this goes like m neutrino square, because it's lepton number. So at the end, it goes at the same. I think probably you can see it as this operator dressing into this by RG evolution, right? This is probably the way to see. You're right. That will give you the yeah. So anyway, this, and if you parameterize this coefficient here, okay, normally this is parameterized. This k over lambda square is written as lambda mu over m square. And the reason is you want to single out the fact that this operator violates chirality, and we know that chirality is broken by moderately small effects in the standard model. So lambda muon is 10 to the minus 3. Okay, it's not 10 to the minus 20. It's 10 to the minus 3. But let's fudge it in. Okay, to be nice and see. And even if you fudge it in, the experimental, okay, this thing here implies that m has to be bigger than 10 to the 5 GeV. Okay, that's quite a remarkable constraint. Okay, so again. Here you have, so that the neutrinos suggest 10 to the 14. Maybe if the couplings are somewhat less than 1, maybe 10 to the 10, God knows, this 10 to the 5. Anyway, scales that are way above our, so this is 100, in fact, this is more, sorry, GV. What the hell did I do? Yeah, GV is correct, then if you go within the same class of effects, you have EDMs.
Are SUSY models supposed to give this generically, or maybe I'm getting ahead?
They generically SUSY model, they do everything. Generically they do everything, and then if you need you worked on this in the beginning, right? At the beginning of SUSY, 83. I remember it. I mean, generically, yes, and then you can think of situations where they don't, right? Like engage-mediated supersymmetry breaking models, right? But generically, in supersymmetry, for instance, in supersymmetric grand unified models, if the mediation of soft terms happens above the scale of flavor, then the soft terms will suck in all the. I mean, there's a scale of flavor where flavor gets decided. But only below that scale, all flavor is encapsulated in the Yukawa couplings. Above that scale, there are other things. If soft terms are already present there, they will pick up all this extra information, and then that's particularly the case in gut theories with gravity mediation. Okay. So another class of effects that comes from here is coming from diagonal effects. If you have diagonal effects here, like electron, and the coefficient here is for some reason complex, that operator violates CP and gives rise to electric dipole moments for electrons or quarks. Okay, so an electric dipole moment for an elementary particle, or better, for a state, for an object with definite transforming under a definite representation of the angular momentum must be proportional by the Wigner-Ecker theorem to the spin. Okay, so the matrix element for since it's a vector, okay, and necessarily must break parity. Okay, so the dipole moment, okay, of dipole moment is defined when you go down to non-relativistic limit. I mean, this operator here, when you boil down to the non-relativistic limit, sorry, I forgot to put F mu nu here. B mu nu, okay. I forgot to put the photon field. The interaction, that operator will boil down in the low energy effective theory to an interaction dE, and dE, I'll tell you what it is, spin times electric field. Okay, and dE will be of the order of k over lambda square, and normally this is taken to be me over some mass scale. Okay. Okay. Again, I'm just parameterizing things in the same way as I did before. Okay, and again, the experimental constraints on these electric dipole moments are very, very strong, and they are improving. Okay, so for instance, the experimental limit on the electric dipole moment of the electron is now 10 to the minus 28 e times centimeter, where e is e. Okay, and it was 10 to the minus 27 only 2 years ago. So there was a big improvement in the last couple of years. Okay, it was stationary for a long time, and these are precisely where condensed matter and fundamental physics really talk to each other in a very important way. And for the quarks, you have slightly less than that. Okay, is 3 10 to the minus 26 here from the EDM of the neutron. If you want to get an idea of how small this is small, think of the electron as an object with a Compton wavelength of order 10 to the minus 11 centimeters. Okay, so the size of the electron, okay, if you want, is 10 to the minus 11 centimeters, and here the size of its dipole is 17 order of magnitude smaller, experimentally. Okay, less than that. Okay.
It's about time now.
Oh yeah, yeah. Can I say? Oh, I can ask a question to the students. So this interaction here. So it's a coupling between electron field, electric field and spin, and as you know, given the transformation property of angular momentum and the electric field, it violates both parity and time reversal. Okay, so this violates CP. Okay, well, it's T, CPT is unbroken, so I violate time reversal, and just because, as I said, by the Wigner-Ricard theorem, you cannot have the dipole moment should be proportional to S. Now the question is, why do we have, in fact, in nature objects like, for instance, atoms that have a dipole moment? Why? What is the trick? Where is the catch? Okay, so I can close the discussion here. Okay. It's a small catch. I mean, there's no.
Why? The question is, why are there dipole moments?
Yeah. How can I have a system that have a dipole moment compatible with CP? Compatible with CPT. Sorry. Yes. Well, these other systems have. Yeah. Sorry. Yeah.
The masses of the leptons are included like in the usual Dirac mass term coupled to the Higgs.
It's
right?
U kappa.
I mean, it's a U kappa, okay. But my question is, why not give mass to the neutron, to the neutrino in the same way?
You cannot.
Oh.
You cannot. I mean, the neutrino. Oh, try to do the exercise.
Oh, okay.
I mean, if you had right-handed neutrinos, you could.
That's
but why do you want to add right-handed neutrinos? Why?
No. So, I mean, I know that left-handed neutrinos haven't been observed, but you can imagine.
Left-handed, right-handed.
Right-handed neutrinos haven't been observed, but you can imagine taking a left.
If you add them, very good question. If you add them,
yeah,
then this nice thing goes away. Wouldn't that be stupid? You can add them and then say that their Yukawa coupling are 7 orders of magnitude smaller.
Yeah,
you could. People do it.
Okay.
Could be like that.
I mean,
it could be that there are right-handed neutrinos. For instance, my colleague